We will try to announce that. But I didn't collect that information. So I'll be the email to everybody that file an email with the slate there with the work and stuff. So anyway, if you are to post that, I can also do.
Oh, no, it's not mine. How can you? No, it's not my presentation.
Oh, that's not yours.
Yeah. So we will make sure you put it in that line email or there to make sure.
I can't see them.
Yeah. Everyone. Both one poster and one.
It's this one.
Most transparent.
And then
Okay, thank you all.
okay.
You can still self-report on that.
Yes.
I'll signal you for 15 minutes.
Okay. Thanks. Thank you for this introduction. So indeed, I'm Pauline Dufour, and I'm working on the Unité Mixte Physique CNRS Thales under the supervision of Vincent Garcia and Stéphane Fusy. And today I'm going to present our recent progress on ferroelectric phase transition in epitaxial antiferroelectric lead zirconate thin films. So this work is in collaboration with Thomas Marossian from C2N, Prime Tekil from Central Supélec, and Alexandre Glotter from LPS. As we have seen this morning, antiferroelectrics have aroused increasing interest for energy storage applications, but also cooling devices. In our work, we are particularly interested in antiferroelectric thin films to integrate them in antiferroelectric tunnel junctions that have been reported for the first time in 2017. And in such junctions, the tunnel transmission is modulated by the transition from an antiferroelectric to ferroelectric state and can be seen as a volatile resistive memory that mimics the behavior of neurons and could be used in neuromorphic computations. Aside from applications, antiferroelectrics are also interesting from a more fundamental point of view. Indeed, for instance, the influence of tensile strain in the stability of the antiferroelectric and ferroelectric phase have never been addressed in thin films, or also the study of new exotic objects that have been reported, such as ferroelectric on-space boundaries, are extremely appealing. However, the switchability of this polarization has never been addressed in such system. So to explore these new perspectives, we focused on lead zirconate, whose structure is derived from the perovskite unit cells. It crystallizes in BPMM or orthorhombic structures. And as you know, it's a room temperature antiferroelectric with a transition to a ferroelectric state around 505 Kelvin. Even though the mechanisms that ruled this transition remain controversial, it is commonly accepted that this antiferroelectricity emerged from the softening of the sigma mode and the R modes, which results in the lead displacements along the 110 directions. They are antipolarly aligned, and from the antiphase oxygen octahedral tilts. So here we elaborated 40 nanometer thin films of lead zirconate by pulse laser depositions on gadolinium scandate 110 substrate, and we use barium strontium retinate as a bottom electrode. So the structural characterization through 2θ omega scan and reciprocal space maps highlights that we have actually two different orientations in our thin films, the 001 orientations here and the 120 orientations, where in both cases, the pink plane represents the surface, the plane of our surface. For the 001 domain, we could extract in-plane biaxial compressive strain of -0.01%, whereas for the 120 domain, it's a bit more complicated as STM measurements reveal that we have actually the 4 different variants rotated by 90 degrees. So basically, we imaged several STM images along 2 different zone axes. And we highlighted the distribution of the different domains that are colored here in blue and yellow. Interestingly, the size of these domains are from 10 to 15 nanometers. And in this configuration, we expect to see the antiparallel displacement of the lead ions. So qualitatively, we observed 2 different 120 domains rotated by 90 degrees from each other. And on the first domain, we could indeed see the antiparallel displacement of the lead ions following the down, up patterns. Whereas on the second domains, which is rotating by 90 degrees, we cannot see anymore these lead displacements. However, we could see columns of oxygen octahedra while here it was only like a single spot, that results from the antiphase rotation of the oxygen hydroxides. So here we have a first glimpse of the antiferroelectric state in our films. We wanted to study more quantitatively the antipolar displacements of the lead ions. So we computed the angular modulations of these displacements, which is highlighted here by the color scale. So here you have 4 different regions measured at room temperature, and you can see that in all of them we can see this antiparallel displacement ions that is that result in these stripy patterns. Here you can see that the displacement is rotated by 180 degrees, and this is due to the coexistence of these different domains. And interestingly, if you look in more details, you can see that all these lead displacements, antiparallel displacement, are uncompensated, which means that we have a quasi-antiferroelectric state according to the Kittel's model. So we have seen that we have we could visualize the sigma and the R modes, which are characteristic of antiferroelectric PBM structure. Now we want to probe the electric field-induced phase transitions. So we perform the electrical measurements at 1 kilohertz on 30 micron square capacitors, and we observe very clear electrical properties, characteristic of antiferroelectrics, with on the IV curve 4 switching peak corresponding to the antiferroelectric to ferroelectric transitions, and to the ferroelectric to antiferroelectric transitions, which gives you this very characteristic double hysteresis loop. So it seems that electrically our films are fully antiferroelectrics. Now we wanted to investigate it in more detail, the polar phase, the electric field induced polar phase by PFM imaging. So first we probe the antiferroelectric phase by applying a 2-volt peak-to-peak AC, and we observe that both in vertical and lateral PFM, the phase is in the noise background, and this is accompanied by no detection at all of the amplitude. Then we add a continuous DC to probe the ferroelectric state. And at 2 volts, we see that we have a well-defined phase and amplitude in the out-of-plane PFM, showing that the polarization is pointing downward. And surprisingly, you also have a well-defined phase and amplitude in the in-plane components, revealing that we have a ferroelectric domains with different polarization components. We observed exactly the same pattern in the negative bias at -2 volts. Where this time we have reversed the polarization from downward to upward. And we also observe this same patchy pattern for the in-plane ferroelectric components. We intended to reconstruct in 3D the polarization through vector PFM. Unfortunately, our attempts were quite unsuccessful so far, probably because of the loss of the ferroelectric memory as soon as you go back to the antiferroelectric phase. But we think that using PFM could be like a promising technique to investigate more precisely the polar state, maybe in thin films that present only one single structural domain instead of our films that have several variants and makes things more complicated. So now we turn to the temperature-induced phase transitions. So we heated up 40 nanometer thick lead zirconate samples from 78K to 473K. And you can see that until 373K, you have a clear antiferroelectric behavior. Then the 2 switching peaks coming from the antiferroelectric to ferroelectric transitions vanishes to lead the place to 2 broad peaks that probably associated to a ferroelectric phase. You can also see this with the linear evolution of the coercive fields up to this critical temperature of 373K, which is further seen with an accident in the saturation polarization at the same temperature. So it means that we have a transition to this intermediate ferroelectric phase, and then we wanted to visualize in real time the displacement of the lead ions in temperature. So we perform STM measurements. We imaged the same region in 5 different temperatures from 300K to 570K. And what we observe is that we have a transition from an antiferroelectric state to finally reach a ferroelectric-like state where you can see that the dipoles are aligned all in the same direction. So here it corresponds to the 100 cubic directions, and to finally reach a paraelectric state. So as a remark here, the ferroelectric state emerges at 520K, which is shifted compared to what we observed electrically. And we assume that applying an electric field additionally to the temperature might reduce this transition temperature. So our experimental observations were supported by atomistic simulations led by the team of Laurent Belaïch, where they implemented in-plane compressive strain similarly to what we observed in our films, and they predicted the emergence due to this compressive strain of a polar phase here in a range, within a temperature range of 150 K, which is similar to what we observe experimentally. Interestingly, both our experimental observations and their simulations suggest an orthorhombic structure for this polar phase, in contrast with the usual rhomboidal or F3T symmetry that is expected and that was observed in intermediate ferroelectric phase in piezo bulk. So we need to further investigate the structure of this polar phase to determine exactly what is its structure. So for the last part of my talk, I will show you how we try to induce tensile strains in our thin films, as it was predicted to stabilize the antiferroelectric phase. So here is I reported the lattice parameters of the standard perovskites. So you can see that in gray, these are the usual available commercialized perovskites that induce a relaxation of the strain for piezo, which is kind of in the no man's land of perovskites. So to induce tensile strain, we resorted to lanthanum luteosate that we elaborated with pulse laser deposition. So we grew thick films of 90 nanometers on dysprosium scanate 110 oriented and strontium titanate 001. And we obtained flight surface with atomic steps, and structural characterization suggests that we have one single domain that can be either 001 or 110 oriented. And to discriminate between these different orientations, we performed reciprocal space maps on 2 films of LLO of the same thickness growing on DSO and STO. And interestingly, if you follow the spots of the LLO here and here, you will see that they evolve in mirror with those of the substrates. And indeed, we could see that when it's grown on DSO, LLO adopts the same orientation 110 as DSO, while when it's grown on STO, it adopts 001 orientation. Interestingly, also, if you insert the spacer layers as barium strontium retenate on DSO, you will see that it kills the symmetry conforming of LLO on DSO, and that this time LLO will adopt the same 001 symmetry as we have seen on STO. So just to summarize, directly on DSO, LLO is 110 oriented, and when it's grown on STO, or as soon as you integrate a spacer layer of a BSRO, you will obtain the 001 orientation. So this is particularly interesting because it means that we obtain a buffer layer with relaxed films, and you can tune their orientations. This is further confirmed by STM measurements, where when you have LLO directly grown on DSO, you see that you have a nomothermic relations between the diffraction spots of the DSO and the LLO, suggesting indeed that we have the same symmetry. Whereas as soon as you introduce even few unit cells of barium strontium retenate, the symmetry of LLO will divert from this of DSO, which confirms this change of orientations. So the final step is to add our lead zirconate on top of this buffer layer. So we grew 80 nanometers thick lead zirconate thin films, and we could see that we successfully managed to induce in-plane tensile strain in our films in the range of 0.2%. And even more, which is even more nice, is that on 8 nanometer thin films, you can see that we have a very, very clear interface with the lanthanum luteosate, which suggests that we can study in details the atomic displacements of the atom from the very first unit cells. And this is what we intended to do with the 4D STEM measurements. So on the left, you have the LLO, and on the right, you have the piezo. And you can see that at the interface, you have indeed a symmetry conforming of the lead zirconate toward the LLO. It will intend to reproduce the same oxygen octahedral tilting. And actually, we have seen that quickly you have a gradient of this oxygen octahedral tilt that emerges. And until 6 unit cell, after this, you have no more oxygen octahedral tilt. in the first unit cell, this oxygen octahedral tilt in lead zirconate gives rise to a polar displacement, which is highlighted here by the yellow ellipses. Maybe it's even more clear on the raw data here. So it seems that in the first unit cell, we have a polar displacement of the lead ions. However, for the rest of the unit cell, it was difficult to probe the antiferroelectric state. Yes, it was difficult to probe the antiferroelectric states of lead zirconate. So these bilayers are promising for the study of the emergence maybe of some antiferroelectric state, but it requires further investigations. So to summarize, we have elaborated antiferroelectric thin films of 45 nanometers. We could see that we have intermediate electric phase that is induced by temperature, whose polar structure as well as the polar structure of the electric field induced phase transition remains unclear. And finally, we have developed these bilayers to induce tensile strain in lead zirconate, and which require further investigations. So thank you for your attention.
Great, okay, great talk, great talk. A lot of interesting results to think about there. And thank you also for showing the relevant simulations for all the labels. Everyone can ask questions. That's it.
Miami University, South Florida. Thank you for the presentation. So I noticed that there is 5 areas to the model, and then the lowest temperature at 0 electric field. But I believe that this is incorporated as antiferroelectric. So what is the explanation for that in the model? Random polarization at 0 field.
You mean at 0 field at room temperature? Actually, it's a tricky question. I don't have a clear answer. I can say that this was also observed in a recent paper by Kiao that was published in 2022, who also observed these uncompensated polarizations. But the origin could stem from maybe like a residual compressive strain in our films, since it's not observed in bulk. So yes, I would say it's from strain. Also, it was shown that the stoichiometry of the films can also affect this emergence, let's say, of an uncompensated dipole. So it could also come from maybe like a not fully stoichiometric in our thin films.
Can you go back to this slide where you showed the recent swoops?
Yeah.
Thanks.
Yes.
Yeah. And so what you were asking about is the fact that doesn't completely close to 0.
Yes, this that we have a small remnant polarizations. Yeah, this I think it comes from this uncompensated alignment of dipoles.
Because I'm going to say because we see something very similar, but we were able to get rid of that by playing with the image. So if you go with 0, 0, 1, we were able to remove that polarization. But if you do different orientation, then it is better.
Okay, so far for us, it was not straightforward to discriminate one orientation from the other one. But when we measured samples with a higher fraction of 1 to 0 orientation, actually, we didn't see any difference in the hysteresis loop. We obtained exactly the same. But so you suggest that if we have a purely 0, 0, 1, maybe we should see like a no remnant polarization at all, is what you observed?
Yeah, we can go with that eventually.
Yeah, okay, thanks.
Mark, saw also experimentalists, you make these kind of exact same things, so. Your areas are very good. We have tried to achieve
Yeah.
right, so we can tweak the fraction of the 240 and the 4 beats. We see it doesn't make a difference. But any hidden polarization in your interface, anything like this, which is going to happen in the samples, we always see a little bit of this.
Yeah. Okay.
So the orientation part, you have to set it up. Like, it's
Okay.
like better before.
Mhm. Okay, thank you.
Hello. Yes, it's community products. I think we very interesting to see the numbers between them going on our station. Because that maybe I don't explain it.
Actually, it's here, we couldn't.
But just to mention that, of course, we know that there is this ferroelectric, I think it can be very competitive, that gives 10 magnitude of centimeters square in normal analysis. And I was wondering that would have shown, let's say, microscopic images where I believe you don't have any clear evidence that the ferroelectric is. But those samples are not the samples. So after you cycle the conceivably, maybe you go to your orthoron before that takes fine. And when you remove it, you will get a stuff in this area. Conceivably. And so this is compatible with what you are seeing in the microscopy, meaning that in the microscopy sample we don't prepare, for example, wrongly without being subject to the switching.
Sorry, can you
The one that you showed the microscopy.
Yes.
Did you switch them before? I mean, did you
Yes, actually, like we checked the electrical properties on beforehand before to prepare the samples, and for the measurements in temperature, when we get back to room temperature, we could observe again the antiferroelectric with the antipolar displacement. So we didn't observe like any pinning of the ferroelectric state in our samples. Yeah. It's just that, sorry, when you apply an electric field in addition to temperature, it seems that you degrade a bit the antiferroelectric properties when you get back to room temperature. But for the STEM images, just heating the sample didn't affect the antiferroelectric properties afterwards.
Time for one quick last question.
Oh, great. My name is Margaret. I'm curious if you use these examples, particularly the ones where you have the variation in stuff. If you ever saw any influence.
You mean the last one?
Actually, for any of the classes, have you ever seen any influence in your peak groups?
Not really, no.
Okay, so I think that, again, thank you for that great talk, great discussion. And we will go back in when let's talk again. Oh, we have half an hour, so there's a lot of opportunity to discuss all the interesting stuff that came up before.
Sorry, I didn't really understand your point.
No, I didn't explain myself clearly, but then you answered very well. But when you show this temperature dependence of the remnant, so this is
Here, we couldn't really see it. Here we go. Okay. I'll plug this guy in.
Yeah, this was an process.
Okay, I was just curious, because I saw the top.